time is it? 29. All right, everybody, a warm welcome here. We're back doing some chemistry. This is Dr. B, and thanks everyone for joining me here. And I see a bunch of likes in there. I appreciate that. And so tonight we're going to do 7 chemistry problems, or maybe 5, I'm not sure. And these are the problems that you're going to see on tests and exams, very much like this. So we want to do that, make sure you're really ready for those. But before we do that, I wanted to show you something and just kind of get your ideas about it here. So let's jump over to my screen here. There we are. Let's go over to this one. Oh, something happened. That's why you don't have that up while you're streaming, because it'll just start playing. Okay. I've learned something new once again. So these are my statistics for my website, or for my YouTube channel. And what's really interesting to me is if you look at my statistics for my channel here, in just the last 48 hours right here, 440,000 videos have been watched. That's quite a few. This point right here, just this 1 hour segment, is 15,000 videos watched just in that time. But what's kind of interesting is right now there's about 15 people or so on the stream. So I think I'm probably pretty good at videos, but really learning how to stream. So any ideas you have for me to improve, drop them in the chat. Let me know. I'm trying to get better at this, just like you're trying to get better at chemistry. And we do that by doing a bunch of chemistry problems. So let's do some. All right, I see clock working is there. Excellent. Who else is here tonight? All right. So we're going to start out and we're going to convert 0.7 moles to liters. Bonnie is here. All right. So the question is, how do you convert 0.7 moles? And we're going to liters, and we have oxygen. Oxygen is a gas. And Bonnie, you're asking, how do I do videos during the summer? I do a lot of videos during the summer. Just do them, upload them, and let them go. All right, so we're going to convert 0.75 moles of O2 to liters. And remember, when we went from moles to grams, we multiplied by the molar mass. Moles to liters. See if you can remember the conversion factor. We multiply by something. And Kimberly, that's a good question. I did a poll on my channel, and people said that half hour was the best time, but I didn't ask when. So asking when might be good. The length seems about a half hour, but when, I don't know. So that's a good thought. All right. Let's do this problem here so we keep you guys engaged in some learning. So if you have moles, 0.75 moles, we know we're going to multiply by something. If it was moles to grams, we just multiplied by the molar mass. But here we have liters. So we have a special factor. It's a conversion factor, 22.4 liters per mole. So whenever you're going from moles to liters, you multiply by this conversion factor here. So let's see how that works out. So if we multiplied, we have moles on the top and the bottom. Those are going to cancel right out, and we're going to be left with liters. That's what we want. So when you're doing this chemistry stuff, you really want to make sure your units cancel out. And when I multiply 0.75 times 22.4, I get 16.8 liters. Maybe you want to make that 17 because we only have 2 significant digits here. 16.8 liters, which makes sense. That's about 3/4 of 22.4. But let me show you another way we could do this. And your teacher's probably teaching you this way. They draw the line here, as Jason calls it, the railroad tracks, and you'll get the same answer, but we consider it 22.4 liters over 1 mole. So we multiply, moles cancel out, and we get the same answer. They just kind of like you to write it this way. But here's why that's kind of nice. What if you had, instead of the 0.75 moles, what if you had the liters starting out? Because here you couldn't cancel the moles out. That wouldn't work. So we say this is 22.4 liters over 1 mole. With the conversion factor, these two are equal. So you could just flip them. You could move this here, and it's still equal to 1 because 1 mole is 22.4 liters, but now liters cancel out and you would get the same, you would end up getting 0.75 moles. So that's the conversion factor thing. You'll see that quite often there. Lots of times teachers will teach you that way. You ready for another one? Where am I at? There I am. Put me back up there so you can see me. All right. So write the electron configuration for calcium 2+, the calcium ion. See if you can do that. Take a moment, give it a try. I'll give you a little help. Bonnie, you may be right. Looks like you actually are correct, because it should be, it forms this ion to get a noble gas configuration, so you have that third energy level full. That looks pretty good. Let's do calcium. Let's write it out. Atomic number is the number of protons, but all the elements on the periodic table, they're neutrals. So this is the number of electrons too. Number of electrons as well. So we know we've got 20 electrons. So we go 1s1, 1s2, and that energy level is full. This first energy level is full. Let's go to the second energy level. 2s1, 2s2, and we go to the P. P holds 1, 2, 3, 4, 5, 6. 2p6. And right now, that energy level is full. So we've got to go down to the 3, 3s2, 3p6. We've used 18. We need to use 20. So down here, 4, 4s1, 4s2. That's calcium. But the 2+, that means that we just get rid of this right here. And it's what Bonnie said it was. And we have this energy level right here full, so that makes it very stable. Hey, Barrick, thank you. I appreciate it. First AP Chem test coming up. Start well with AP Chem because it'll snowball on you, and that will make things difficult later on. So, Jason, you put argon. It would have the same configuration as argon. If you were going to write it condensed, you would probably write, not sure if you would do neon and then put this at the end or not. Hello, Pratasha, and Kanisha's here as well. I have a lot of videos, Kanisha, for electron configurations, and I think there's one in the description for this, but if not, put a comment to this, this video when it's over, and I'll put some stuff in there for you. So that's the deal here. What's real important to understand is that it lost these 2 electrons so it could have this full outer shell. So I might even have a picture of it. Do I? Yeah, let me get this picture up because it's worth looking at. So here's calcium right here in the middle of the screen. And these 2 electrons right here, these are the valence electrons. When it loses these, it's like it loses this whole shell here, and now it has 2 4, 6, 8. And that's really stable. That's why it lost the 2. It lost them to get rid of this shell, so the shell underneath was full. Yeah, Jason, that's the way I would write it. Is that neon, and then the brackets around neon, and then the end of it. Okay. Well, let's talk about your teachers might have shown you how to do it with this diagram here, but I don't really like this diagram because it doesn't show you how you have your S block, your D block, your P block, and down here would be your F block. So I really like this, and there's a video in the description on how to use this, I think. All right, well, let's look at calcium some more here. Calcium some more. Oh, excellent, Kanisha. Glad you found that. Which has a larger atomic radius and why? Magnesium or calcium? And what they'll ask, especially if you have that AP test coming up, they love to ask the why on there. So where are we at? Calcium, magnesium. Which one has a larger atomic radius? So if you think about what's happening here, when we looked at calcium before, bring it back over here. Let's make it a little smaller. When you go down, this is the first energy level, second, third, fourth, and fifth. So you're adding levels each time you go down. So which is going to be bigger, magnesium or calcium? Which one has more levels? 3 or 4? Calcium is going to be bigger because it has more levels to it. It has more energy levels, more electrons, more shells. Jason, like you say, calcium is larger. So as you go down groups like this, any of them, we're adding energy levels. That makes them bigger as you go down. So when you're changing, there's a question about the 3D. So when we start getting into the 3D, you can kind of think of these as similar energies. So they're kind of very similar. We kind of ignore the D block quite a bit. So like if you're talking valence electrons, you're really talking the S and the P electrons. You kind of ignore the D electrons. So I hope that helps. Levert. I hope that helps explain that. All right. So what's kind of interesting is when you stream, they say never look at your analytics because it'll mess you up. But I still look at my analytics occasionally here, and so there's 17 people here right now, which is actually pretty good for me. So it's kind of interesting to watch. Now there's 18 people, so I don't know how that's happening. It's kind of a weird thing when you're streaming. You imagine all these people out there. So right now I'm imagining all you out there thinking about chemistry, and it's kind of a strange thing. So let's talk about some other strange things. How about Lewis structures? Because that's kind of something you see a lot of, and you use it for other things. So you'll have a question that you just need to know how to do Lewis structures for. It might not even be about Lewis structures. So give this one a try. And I love Lewis structures. It's probably my favorite thing in chemistry. I've done probably every Lewis structure there is a video for that. OF2. And I gave you the rules right here to help you out. Yeah, Jason, you said atomic radius is the opposite of electronegativity. Yeah, I would agree, because fluorine's the most. When you go up, fluorine is the most electronegative, so, but it's pretty small. So Lillifert, I'm trying my hardest there. 4p, I would say 4p I think 4p is a higher energy, but they're all in the same energy level. So 4p and 4s, those would be your valence electrons. Jason says trend-wise. Okay. So like I said, I love Lewis structures. I can do Lewis structures all day. For some reason, they're just like little Sudoku puzzles for me. All right, so OF2 is the formula we're looking for. Let's see if I can draw it. So we count the valence electrons. So what you have to do to count valence electrons, that's your first step, is group 1 has 1 valence electron, all of these. That's that S1, right? 2 valence electrons, S2, it ends in S2. And then you go to 3, 4, 5, 6, 7 valence electrons, and then the noble gases have 8, except helium, which is 1s2, and it's used all its electrons, so it's full with 1s2. So oxygen has 6, fluorine has 7, but we have 2 fluorines there. So 6 plus 14, what, 20? Nif, I can put a link at the end of this to C2H6 in the chat. If you remind me at the end, I'll do that. That might be the easiest way. All right, so let me get rid of this. So we got our valence electrons, and actually we want to put the least electronegative. I will look at that in a minute. Get rid of all this stuff here. Okay, so then you write a skeleton, and the key is the least electronegative element goes in the center. And Jason, you were just referring to this. Fluorine is the most electronegative element on the periodic table. So fluorine is more electronegative. Oxygen's right next to it, but it's pretty electronegative, but fluorine is the most. So we know the fluorines are going to go on the outside of our Lewis structure there. So we'll put oxygen in the center, fluorine on the outside like this. We've got 20 valence electrons. So we'll put a pair of valence electrons between the atoms. Let's move a little closer here. That's a very poor looking F. There we go. And these electrons right here, that's the chemical bond. These are bonding electrons. They're the ones that are shared between the atoms. Then we put a pair on the outside. So we want to get 8, the octet, like this. So we have an octet here and here. We've used 16. So we have 4 more. We complete the octet on the center right here. We've used all our valence electrons, and that's the Lewis structure for OF2. We've used all 20 valence electrons. Octet here, octet here, octet here. That's it. How's that look? So remember, you really need to know the trend for electronegativity. Just remember, fluorine is the most. If you go towards fluorine in any direction, things get more electronegative. All right. Let's try some molecular geometry. And I'd like to show you, this is an app, and it's a free app, and it's probably one of the best ways to really understand molecular geometry that I've ever seen as a teacher. So we're going to look at OF2, and remember we have 2 lone pairs and then 2 fluorine atoms on that central oxygen. So molecular geometry is always on the central atom that we base it from. All right. Okay. Thank you, Niru and Mackenzie there. All right, let's see if I can get this to come up on the screen. Too many things. All right, I'm going to open a web browser here. So it's called PHET. And so here, that's our central oxygen. So do you remember how many fluorine atoms there were? Single bonds, right? 2 of them. 1, 2. So, and you see they push away. That's that valence shell electron pair repulsion. You can't get them next to each other. If you think about it, you have your fluorine atom, the nucleus in the center, and around it, those shells, those are electrons. So there's like this negative cloud. So these two, they don't want to be next to each other. Now the lone pairs. And lone pairs, they occupy space. They have volume. So they're going to push things down. Try to imagine what that's like if there's something here pushing these down. There it is. So now it's kind of made it bent, and we're going to put our last lone pair on, and boom. That's the shape, the molecular geometry of OF2. Molecular geometry is called bent. Electron geometry would take into account these guys here. Electron geometry would be tetrahedral. So how do you know that this is bent? That's the big question. So let me drop the link in chat so you guys have it there. I really strongly recommend you play with this. It's a lot of fun. You can like remove the atoms and add lone pairs. You can do crazy stuff like put a bunch of lone pairs on. I don't think this exists, but it does say octahedral. Anyway, let's go back to our screen. Bent, and yeah, you got the electron geometry, Jason. Bent's the molecular geometry. So here's kind of a way to think of it. If you have four things, hello, who's Saifa from India? Awesome. I've never been to India. I'd like to go. I had a very close friend when I was young from India. So we have OF2, and if you remember, we had the fluorines. That's our single bond. That's a pair of electrons, and we had a lone pair up here, and then around like this. Draw it in there. We have 1, 2, 3, 4, what we call electron domains around it. We have 2 lone pairs, and like Jason was saying, it's bent. The ideal bond angle is 109.5, but it'll be different. It's never really 109.5. It's just like water here. So if you want practice using this and that app, there's a link in the description for this stream here, and that will really help you get it. So the other way you can do this is called the AXE. Your teachers might be showing the AXE notation. And what they say is A is the central atom, one of those. X, that's the actual atoms bonded. We have 2. E, those are the 2 lone pairs. So you would get AX 2E2, and you'd look that up kind of on a table like this, and it would tell you that it's bent. And there's an example of how to do that in the description for this stream here. So how are we doing? We actually have more people than usual on the stream tonight. So I don't know if people are staying or new people are coming in, but it's kind of cool. Josefa, you're asking how to improve your chemistry. I think the big way to improve your chemistry is work a lot of problems, but then get a solution. So I would work a problem and then like watch one of my videos or someone else's videos, see how they do it. And if you got it wrong, figure out where you got it wrong and work that same problem again until you get it right. And that's really my recommendation. And study with other people. That's always awesome. Okay. Let's do 2 pH problems, and we're going to call it an evening here. So how about pH of a 0.01 molar solution of HCl, hydrochloric acid? I'll give you some help. This is an equation you should memorize. All right. So whenever you see pH, a lot of students don't know this. I think it's kind of interesting. It was interesting to me when I was learning chemistry. The H, that stands for the H+. That's right here. When you put hydrochloric acid in water, it'll break apart into H+ and Cl-, aqueous. So pH is really the H. That's what we often consider things to make an acid. If you see an H in front of something, it's probably an acid. So all we have to do here is take the negative log of 0.001, and if you do that, you end up with 3. That's it. So the pH is 3. So we know that this breaks apart completely because it's a strong acid. Good to memorize that. And we just take the negative log of the molarity. We get 3. pH of 3 would be an acid, which makes sense. We have hydrochloric acid, right? Jason, make sure that's a small p there. This p tells us that it's the negative log. Kazakhstan, wow. I had a friend that actually lived in Kazakhstan for 2 years. Seemed like a pretty neat place. All right, so here's the hard one. We're going to wrap up with one to test your chemical ability. Find the pOH and the pH, both of them, the pH and the pOH of sodium hydroxide. And you're correct, Jason. Strong acids dissociate completely, like HCl, HNO3, H2SO4. These are good ones to remember. HF is not. I think HBr is. These are the ones you see all the time. All right. These are equations you must know if you are going to do well on any chemistry exams. They're the ones that, along with that pH one, got to know those. Where's that pH one? I'm going to bring the pH one down in case you forgot it. All right. So, interestingly, if you take the pOH, it's just the negative log of 0.001, and you already know the answer to that. 3, right? And NaOH, this is a strong base, so it'll dissociate completely. So how do you find the pH then of this 0.001 molar solution of NaOH? Got to use this equation, right? Hey, Mohammed. Hey, I'm glad I could help you out. It's my pleasure completely. For some reason, I really enjoy doing chemistry problems. So I figured just put them on videos, right? Okay, so we know that the pH plus the pOH equals 14. We've figured out the pOH. We don't know the pH. So something plus 3 equals 14. Not real high level matrices algebra or anything. 11, right? So the pH of this 0.001 mole solution of NaOH is 11. And Jason remembered to keep the p a small p this time. So good work, Jason, on that. Let's see what time we got here. Whoa, we've been doing this for a while. So I think that's about it for me tonight. It was kind of a good evening if you're looking from a statistical standpoint. Had, I think, probably the most people I've had for a while. It's still not, see if I can find this again. There it is. We're still not getting, say, 15,000 people, but it's a good start, right? Caps lock. Thank you. All right. So I will be back on Thursday. I think I'm going to start just doing Tuesdays and Thursdays. That way I can prepare more because I have another job at a university here. So that kind of eats up times at certain points. And I like making lots of videos. So thank you everybody here for spending time with me this Tuesday evening. And good luck with all your chemistry stuff and everything else. I'm going to stick on chat for a bit, but I'm going to end the stream. As always, this is Dr. B, and thanks for watching.